last lecture of additive manufacturing, MSE 5223. This particularly relates to metal additive manufacturing. I'm going to be posting a number of documents related to this particular topic. So you can take a look at that and read through this topic in greater detail. The reason is that there are so many new developments taking place, especially in the case of metal additive manufacturing. For example, if I don't know if you have gone and looked at some of the new equipment that have come on the market, which are pretty inexpensive compared to the other types of metal additive manufacturing equipments. Um, this is by Markforged, so you should go and take a look at that. So it's a kind of a desktop equipment. So, but you may not be able to get the same kind of property that you get with the regular type of equipment. But in any case, I do not want to overburden you, especially at this late stage. So I'm just going to give you a flavor of metal additive manufacturing. So, in the last lecture, we talked a little bit about direct write technologies, and in the current lecture, we are going to talk about metal additive manufacturing. So, uh, I have uploaded the reference related to the NIST workshop from December 2012. It is called Measurement Science Roadmap for Metal-Based Additive Manufacturing. And why did NIST do this? If you ask me, the reason is that I have talked to the people from NIST, and they tell me that metal additive manufacturing is probably going to be having the most impact among all additive manufacturing technologies. So they really paid a lot of attention to that. They had a workshop, and I believe that they might have had more recent workshops, or they might be having some in the near future. I believe that uh, somebody else also, Sampi, has metal additive manufacturing workshop in coming up in June. So if any of you are interested, you should try to go to that one and see what is going um, uh, to be taking place in that. And according to this report, and I believe that these challenges have not changed. Those are related to what are the materials that we are going to be using for additive manufacturing, what are the processes and equipment, what is the qualification and certification that we require, and most importantly, what is the modeling and simulation that we require for additive manufacturing. For metal additive manufacturing, it is more important, but the modeling and simulation is more important for, especially for metal additive manufacturing. So, if you look at it, what are the important tasks in front of us? Important task is we need to standardize the AM processes, and it is the most important step for advancement of metals additive manufacturing. And I was told that I read that the ASTM committee F42 was formed in 2009 for development of international standards, and they developed the spec for AM of Ti64 with powder bed fusion in 2012. And the 2792 standardized AM technology was approved in 2009, but I do not know the exact details, but I was told that it was cancelled later. And the other important thing that took place in as far as ASTM standards is they have created a specification for AM file format, which allows the designs to be transferred between different hardware and software systems. So if example, if you use SolidWorks and create a .sml file, that needs to be read as easily by an RCAM equipment as um, a wire feed system or Shiaki system. So in order to do that, they created a standardization of the AM file format so that it will have the same information that can be read by all different pieces of equipment. So what are the different metal AM technologies? There are basically whether it is how the uh, energy is being delivered to the material, whether you are using a binder or whether you are using a laser or whether you are using a heated nozzle, etc. And it is also possible by the group of materials being processed such as plastics, metals or ceramics. And the easiest way to define that is by the feedstock state, whether it is powder, wire, or sheet, or whether the powder is being delivered in a bed that is being moved, or whether the powder is being delivered through a nozzle, heated nozzle, or not. But this classification does not contain some of the newest machines, such as those made by Markforged. So here is a list of representative AM equipment sources and specifications. I know that there is quite a bit, but pay attention to the build volume. Okay, so the larger the piece that you want to make, the component that you want to make, then you have to choose the right one. But then your cost also goes up. So that's the give and take that you have to have in order to choose the right kind of equipment, the right kind of feedstock material. Among all powder bed systems, at least till 2015, they were all manufactured by companies outside the US. And in general, build volumes are less than um, about 300ths of a meter cubed. And RCAM produces the only powder bed electron beam system. Of course, I mean, this one, I mean, if you look at it, the whether there are some, I mean, this one really doesn't contain the SLS type of equipment. So that one is a little different. So we are only talking about powder bed systems that are different from SLS or the selective laser sintering technique. So here is a schematic of a powder bed system. So in this case, it is pretty similar to the SLS technique. So you have seen this in the case of the SLS technique. Okay, so again, it's pretty similar to that, but it is a lot different in the case of the laser capacity and the powder bed capacity, etc., and the build volume. So pretty similar to the SLS technique. It is created by raking the powder across a work area. You have a electron beam or laser beam programmed to deliver the energy to the surface of the bed, and it is melted or sintered into the desired shape, and then you put more powder across the work area, and then you repeat the process to create the solid three-dimensional component. In that case, it is pretty similar to the other 3D printing or additive manufacturing techniques. The electron beam or RCAM, this is a technique that is being used for building by GE in Europe. I believe that they have a plant in Italy for making turbine blades. So if you go to their website, if you go to the GE Tech website, you will be able to find a video that describes that shows the process. So in this case, it's an electron beam that melts the powder together to form the final part. So in general, the layer thicknesses are 20 to 100 microns. So which means it is 0.02 to zero point 0.1 millimeter. So you can understand that this is very accurate, but in the case of the SLS and things like that, SLS and similar processes, the powder bed thicknesses used to be much bigger than that. Like, it can be as much as half a millimeter or 500 microns to 1 millimeter. So, and one important difference between the previous techniques to current techniques is that many of the newer machines can have more than two or more lasers with different power under inert gas atmosphere. Some of the advantages of the powder bed systems are that you don't need a support material. The powder bed itself is a support material, and the internal features can be created easily, and there is pretty good dimensional control and minimal distortion by controlling process parameters. The direct powder bed system is different from the powder bed system. So you are directly delivering the powder to the melt area. So they call it, it is commercially available under different trade names. It can be called selective laser melting, laser fusing, or direct metal laser sintering, etc. And the only exception is the electron beam melting process, which uses an electron beam under full vacuum. So it doesn't use a laser, but it uses an electron beam. So this one, one of the common ones is Optomec, and we have a unit that is made by Optomec at our OSU Stillwater location. So if you want to take a look at that, or if you want to use it, you may be able to come here and use that. And it is more easy to attain volume buildup than powder bed systems. So it's pretty large volumes, large build volumes than the powder bed systems. So this is the general schematic of a powder feed system. So there is a deposition head, and you create that. So what is the other difference between the powder feed system and the powder bed system? The powder bed system does not need a substrate. The powder feed system needs a substrate. So which means that after this component is made, you have to slice it off of the support material. So which means that you have to have the right kind of support material. You have to start preheating it, etc., etc. But in the case of the powder bed system, you do not need to do any of those kinds of things. So in this case, the powder feed system, the powder is conveyed through a nozzle onto the build surface, and the laser is used to melt a monolayer or more of the powder into the shape desired, and then you repeat the process, and then, as I said, you need to have a substrate to support the material. So what are the different types of powder feed systems? One is you have a workpiece that remains stationary, and the deposition head moves from place to place. or the deposition head will remain in one place and the workpiece is moved. And the advantage with the second type of machine is that you have a larger build volume and you can refurbish worn or damaged components. So if you are going to be repairing a piece of equipment, you can build up the material on top of an existing worn out component or a fractured component. Then you have a third system, which is the wire feed system, and the most common one is called SCIAKY or SCIAKY. And there are some videos that I have posted, video links I have posted, so you can please go take a look at that. Okay, so the feedstock is a wire, and the energy source for these units can vary from, it can be an electron beam, laser beam, or plasma arc. And initially a single bead of the material is deposited, and then you build up the three-dimensional structure with subsequent passes. And one big claim that these companies are making is that they can make entire components using the wire feed system. For example, Lockheed Martin is claiming that they can make this component, make their satellite components, entire satellite components, using the wire feed 3D system, 3D printing system. So this is an example of that. So you have a wire feed. So there is a third feed material. You have a substrate, and then you have an electron beam gun, and that electron beam will melt the material and build up the material part by part. So here are some feeds. It's a little bit of a PR type of a video, but there is a lot of information here also. So you can take a look at that. I mean, I would recommend that you take a look at this. So what are some of the advantages is that you have a high deposition rate. You can have large build volumes. You can make entire components with that. And the disadvantage is that you do not get a very good surface finish, so which means that you need pretty extensive machining than powder bed or powder fed systems. So in all the three methods, these are some of the most widely used materials, and most common one is the Ti64. Then they have the Inconel 718. There is a lot of stainless steel 316L, 304, etc. being made using 3D printing. Some aluminum alloys like Almag silicon or aluminum copper precipitation hardenable materials, some intermetallics, and then some magnesium alloys also. So the disadvantage with aluminum and magnesium alloys are that, especially in powder form, they are pyrophoric. So you have to have an extremely well designed and fire resistant equipment in order to be able to make components using these alloy systems. So what are some of the parameters influencing metal AM part properties? Whether it is powder bed, powder feed, or wire feed, how you are transferring the energy, what is the beam shape, what are the processing conditions, what shielding gas, whether you want vacuum or not, and then whether you have to have preheating. One of the things that I have not added here is what is the post-processing that is required. For example, in some cases, after you make the component, you have to do hard isostatic pressing in order to be able to completely eliminate any kind of subsurface defects or subsurface porosities. Then the other condition is what is the alloy powder shape, grain size, and size distribution, etc., and powder impurities. whether you need the powder to be preheated or the substrate to be preheated or not, you have to take all of that into account. So what are some of the problems with AM of technically relevant metal alloys? Um, the first and foremost is that the microstructure is going to be dependent on the heating and cooling rates. And in this case, you are going to be doing fast heating and cooling. So you are suppressing, I mean, you may need to do that because you may want to suppress certain phase transformations. Um, and whether there are going to be supersaturated phases or not, we don't know. Then, if you do that, you may have some kind of segregation of impurities or segregation of gases, etc. And in some cases, you may have hot cracking. Then, because you are heating and cooling, you may have thermal residual stresses. One thing to note is that you are directing heat flow in one direction only into the building plate or substrate. So which means that you can have textured grains and you will definitely, most definitely have anisotropic properties. And after you build one layer, it is going to go down and then you are going to be building another layer on top of that. So even though it may not, that layer may not go to the same temperature as the melting layer being melted and joined, it is still going to be undergoing repeated heating and cooling cycles. And in this case, if there are going to be phase transformations taking place, those temperatures can exceed liquidus temperature and some phase transformations, etc. So you need to really take into account whether or not there are going to be multiple phase transformations in complex microstructures and whether or not you're going to have thermal residual stresses and what do you need in order to eliminate those thermal residual stresses. For example, this is the thermal profile of a single layer of Ti64 during additive manufacturing. So this is the this is degrees Kelvin. This is the temperature at the top layer, and as you take it away from the melting point, I mean from the topmost layer, you're going to have some kind of a gradient in temperatures. So that's going to have some kind of a residual stress and all kinds of associated problems with that. So you need to understand what are the phase transformations going to take place in multi-component alloys under additive manufacturing conditions. And you must understand them and you must control them in order to get repeatable properties. You need to have a good knowledge of stable and metastable phase diagrams. You need to have knowledge about the thermodynamic and thermophysical quantities required. Then if it's going to be heated and cooled, you're going to have diffusion processes being active. So you need to know what are the diffusion kinetics and what are the mobilities required in order to get the right kind of microstructure. So here is a general schematic of the whole process and what information is going to be fed into this big black box. So what are the steps in the alloy development? The first level test is you need to know what is the effect of the high cooling rate on the material. So for that you don't need to take a powder itself. So you can take a block of material and you need to have some kind of a rapid cooling equipment. You heat it up and then you cool it at the rate at which you are going to cool during the AM process. So there the processability is only a function of the alloy. Then you need to have an intermediate test and you need to know what is the alloy behavior during rapid melting and cooling using the AM equipment. So again, here again, you don't need the powder but you need to know that your processability is going to be a function of the process as well as the alloy itself. And the ultimate test is going to be based on additive manufacturing of the powders itself. And so there you need to optimize the processing conditions of the AM equipment, and then you need to know what kind of microstructures you are going to obtain as a result of the processing. And most importantly, when you are going to be using different shape powders, you need to make sure that the powder shapes, so when you shake a powder bed together, you're going to have a certain powder bed density. And that powder bed density is going to define your final properties. So if you had all perfect squares and powders of different sizes and shapes together, you really may need to have three different powder sizes together, so that you have the big powders together, and that will probably give you 74% powder bed packing density. Then you have smaller powders that will go in between that, and you have even finer powders that go into this, and you may even end up getting about 90 to 95% powder bed density. So, but what is the difficulty with that? The higher the powder bed density, the less flowable it is. Okay, and if you want to really know about the effect of powder bed density, I mean, for metals, especially metal AM especially, you have to understand the effect of powder bed density on the final properties. And I will recommend that you should go and look at the papers by Rand German, R-A-N-D German, German. He used to be a professor at, I believe, at Rensselaer Polytechnic, and then after that, I believe he is currently uh, at Penn State University. So you may want to take a look at his papers, and I will also see if I can get some of those papers and post them for you to take a look at. So in this case, your final processability is going to be dependent on the process, the powder, as well as the alloy. All three are going to be affecting your final properties. So why are we interested in an intermetallic alloy such as titanium aluminide? First of all, it is because it has got very low density, it's got extremely high Young's modulus, high strength and creep resistant. And most importantly, it is oxidation resistant than titanium alloys. So because of that, it has higher service temperature than standard titanium alloys. It is, but the difficulty is that it is fully intermetallic, which means it is very low elongation to fracture. It is brittle at room temperature. It is sensitive to contamination, and the properties are strongly dependent on phase morphology. It is extremely difficult to process by additive manufacturing. So here is an example of that. So some of the blades and things like that can be made using this particular alloy, and the green area is the titanium aluminide, which is something that we could use for making turbine blades using 3D printing. So what are some of the different microstructures that you can get as a result of additive manufacturing from metals? So if you remember, or if you recall, I had said that if there are fiber reinforcements, even chopped fiber reinforcements, when you extrude them, those fibers are going to be aligned in the direction of the extrusion. Similar to that, you're going to have different microstructures in different directions if you are going to do metal additive manufacturing. So in this case, you can see that, I mean, I don't know if you can please expand it, you can see see the effect of this. In this case, the materials are produced by Applied Research Lab at Penn State. It is done by laser beam melting, and it's called the powder blown system. And the third one is produced by NASA Marshall's electron beam wire fed system. So in all these cases, you're going to have some kind of a columnar grains, and there could be more columnar grains in one type than the other due to the uh, heat extraction in one direction. So heat is going to be extracted in the direction of the nozzle movement. So here is the not scanning electron, it's optical micrograph of the laser powder blown produced Ti-64 in the as fabricated thing. And if you look at this cross section, you can see that it is different from this, and you get more of an organized structure here than here. So that's the difference, and it can lead to differences in mechanical properties. So in this case, the laser powder blown material appears finer in structure than those produced by the wire fed system. And they speculate that it is because it has got larger melter pool, has slightly slower cooling rates in the wire fed system than in the other case. So if you have a laser powder blown material that is being produced by a slower cooling rate, you are going to have a much more coarser microstructure. In the laser powder blown, you are going to have heat deposition or heat supplying of the heat as well as the extraction of the heat at much faster rates. So that will lead to a much finer microstructure. So here are some examples. Again, this one reinforces what you saw in one of the earlier slides. So what material systems can be used for metal additive manufacturing? I like this table better than the other table. That's why I put this up again. Okay. So what are some of the issues related to metal additive manufacturing? Most importantly, the alloys have a very complex thermal history, and because the microstructure is going to be different in different directions due to the heat extraction and the heat uh, uh, supplying of the heat, and due to repeated melting and rapid solidification, you're going to have a very complex thermal history. So because of that, you are also going to have repeated solid state phase transformations, especially if you are in that close to that temperature range. These factors will introduce complexities not typically found in conventional processes. So, and the other thing is that because you are going to have melting and rapid solidification on the surface, if you are going to be making this under an inert gas, that inert gas can easily be absorbed or adsorbed by the molten metal pool. So that molten metal pool can create subsurface defects, which in turn can affect fatigue properties, because those fatigue cracks can start from those points rather than from the component that is made by additive manufacturing. I'm going to be listing some of the mechanical properties here. So in many cases, you have to have post thermal processing. So you have to have some kind of a hipping or thermal annealing treatment, because that is the only way you can take away the anisotropy of the material. So for example, if you are going to be doing hipping, you are going to normally do that at 100 megapascals at 926 degrees centigrade, so that, I mean, why do you do hipping? Hipping so that if there are any kind of defects on the subsurface, they will all get completely removed. You may also do thermal annealing so that any kind of anisotropy in the microstructure can be eliminated. So here are some, so powder fed systems, you can see that these properties are reasonably uniform in all different directions. But the powder fed system, and let me come back to this, but the powder fed system, there is more anisotropy in the different directions as a result of additive manufacturing. So what are some of the differences in the powder fed systems and alloys that are made, I mean, as prepared wrought alloys? Um, Yield and ultimate tensile strengths of AM process alloys, especially in the direction of the additive manufacturing process, far exceed the typical value for a wrought alloy, because wrought alloys are typically isotropic, whereas in the case of anisotropy, they are not the same. So because the strength is higher and the yield strength is higher, the ductility is slightly lower than the wrought alloy. And there is anisotropy associated with the build direction, and there is slight anisotropy in yield strength and ultimate tensile strength associated with the build directions. So this is what I have said. So again, the fatigue properties are going to be different in the as fabricated and the hipped samples, or hard isostatic press samples. So you can see that by doing hard isostatic processing, you're going to be taking away some of the subsurface flaws, and that clearly leads to an improvement in the fatigue properties and the mechanical properties. So what are some of the effects of surface roughness as a result of the additive manufacturing technique and uh, the properties? So in this case, what they found was that the higher the surface roughness, the lower the fatigue life of these materials. So if hipping or harder static pressing is added to the part after additive manufacturing, it improves the mechanical and fatigue properties, because those subsurface flaws are going to be eliminated as a result of hipping. But a hip is an expensive piece of equipment, and not everybody has that equipment available to them right away. So when you make components using additive manufacturing, I mean, this is more important for metal additive manufacturing, but those same questions can be asked for every single additive manufacturing process. So the first question to be asked is, has the technology been developed and standardized? And so it's not enough to just make the material, you have to make them in enough numbers, and you need to characterize them, and you need to standardize them. And whether or not you are going to be using B basis or A basis is entirely up to you. But sometimes the final user of the components is going to say whether or not which basis has to be used, and which industry needs these components. If it is aerospace, most definitely these are going to be used. I mean, these A bases or B bases at least is going to be definitely used. And the third question, third and final question, has the materials technology been demonstrated and um, demonstrated in an actual relevant operational environment? So that's very, very important. So here is a listing of the challenges and constraints in table form. You can take a look at that. And the other one is from the NIST report. So what are the challenges and constraints for widespread adoption in all four different areas of additive manufacturing? From additive manufacturing materials, additive manufacturing processes and equipment, qualification and certification, and finally modeling and simulation. Okay, so what are the big picture possibilities? It has a possibility to make local manufacturing of products which becomes normal. Then small businesses can successfully compete with big companies, um, and parts are produced closer to home, which will cost the same as those made elsewhere. So you can completely eliminate the shipping cost. Uh, you reverse increasing urbanization of society. I mean, I think it might be a stretch. I have taken it from somewhere, but I don't know if I completely agree with that. But I do agree with the fact that it can make jobs resistant to outsourcing, and creativity in design becomes more important than labor cost for companies to be successful. So that I believe is about it, and I will be posting some uh, additional papers to D2L. I really enjoyed teaching this class for you guys, and I hope that you have had an opportunity to learn something new here in this class. Okay, thank you, and have a wonderful summer vacation if you are done. Otherwise, uh, have a good summer month. Have good summer months. Okay, talk to you later.